Greetings all. It's such a humid day today. I'm just sitting in my pajamas because I just couldn't deal with the trackies. Even the trackies were like a step too far, and so I just yeah. I said at the end of the last sesh. Actually, now that I've said that, I should check that I updated yeah, this looks correct. It should really be in black because otherwise it doesn't show up correctly. So I'm just going to fix that now. I mean, it would be great if it had an outline as well, but I'll fix that later. Okay, cool. Yeah, like I said at the end of the last sesh that I wanted to do a kind of summary of where things are at the moment, because I was kind of starting to feel like I was banging out the tasks, right? So we did, MapReduce part 1 and part 2. Finished them, got them tested and everything, but I was sort of thinking like, oh, did I actually learn anything when I did this? So yeah, I went back and looked up the MapReduce paper, which is, explains it better. To be honest, it explains it better than MIT's course does. And I'm not going to go through everything, like reading all of it or anything, but I'm just going to show that, that one picture that I said I was looking for, like a diagram that just explains everything. Well, fuck, here it is. The promised diagram. Yeah, so I'll go through it quickly, just because this does quite a good job of summarizing everything. There's quite a bit of activity happening outside at the moment, just people sort of rolling through, going like, yo, bro. I mean, fuck knows what they're doing outside. It was pissing down like an hour ago. It's just massive. There's actually thunder. I thought we'd have thunder on the stream again, but never mind. Yeah, sorry for being 5 minutes late starting as well. I think 5 minutes is acceptable in Twitch culture, but never mind. So when I was sort of trying to visualize MapReduce as a full-on program, this step is what I guess I didn't mention. Having the user program, the thing that the user interacts with, runs their own program on their own computer, and then that starts spawning like computer programs running master, worker in like lots of different computers on the cloud. And then those coordinate amongst themselves in order to process the user's input files into output files. So that's the basic structure of the diagram. User program, input files, output files, and like a bunch of stuff. I'm trying to circle it here. Oh fuck, I circled too intently, like this stuff. So we'll try to summarize how all that works. Master and worker, of course, loads of masters, loads of workers, and they're all up and running. In the first place, we haven't actually yet looked at all of the stuff that's going to control how they work, which worker gets to do which piece of work, and how the scheduling works and all that stuff. That's not been that's really like the third part of the project. So the fourth part. So the third part is like doing the distribution of the tasks onto all of the workers and things, and number 4 is handling the failures if things go wrong. So we haven't looked at that yet, so I'm not going to talk about that. Instead, I'll just do a summary of what we have actually done, which is what this actually means via the word count example, because again, that's what we just did, right? Just going to check that we are indeed live. I haven't changed anything. This isn't like one of those fake broadcasts with broadcast what was it that makes it a fake broadcast? Like bandwidth test equals true or something like that. I'm always kind of paranoid I left that in and it's just not going to show up, but should be okay. Always get distracted when someone opens and closes these windows. Just banging noises. Cool. So in the word count example, the input files we were looking at are literally just these. I'm going to show them in Visual Studio Code, which is still lagging like a bitch. Main, here they are, these files. PG, Being Ernest, Dorian Gray, Frankenstein. So these are ebooks. I think they're full ebooks actually. They look pretty long. And yeah, so those are the input files. The outline of what this is. We said there's a map phase, a reduce phase, files, and files. So okay, I should be pointing with the mouse. Files get processed by map. Files get processed by reduce. Files. So the input files. Well, what is the map phase expecting? Each of the map tasks, as we defined them, right? So we've looked at the input files. The map task was coded up in MapReduce common map. So you can see from the signature here, do map runs a single map task. So I know it said sort of earlier, oh maybe do map runs more than once on one map task, but in the paper I didn't see any mention of that, so I'm just going to say no, every map task, do map goes once on the map task. It processes an input file, so every input file corresponds to a single map task, right? The input file gets sent into the map task. So in this case the input files are single, so the actual map function takes a single key. So I mean, we said that the data structure that handles pretty much all of the data in the entire process is key value. So like there is a key and there is a value, so the key tags the value. It's like what we said about the dictionary, how you can have a dictionary with keys and values, like as another example off the top of my head, the keys are names of Pokemon species and the values are the families. So Bulbasaur key gets, the value of that is Bulbasaur. Ivysaur, the value of that is Bulbasaur. Metang, value of that is Beldum. Didn't want to include Gen 3 examples because who the hell knows Gen 3, but it's the first one that popped into my head, so fuck it. And yeah, so the raw map function, the function that do map applies, is something that accepts a single key value unit. So key value are like atomic units of data in this setting. So do map is going to process quite a lot of those in principle. It could process a lot, but we said do map is a single map task and that comes from a single input file. Well, in the word count example, a single input file every input file contains a single key value. The key is the name of the book and the value is the contents of the book. In a more general setting, I guess an input file could contain multiple keys and values. It doesn't matter. In principle, the raw keys and values are split among some input files. Each input file goes into a map task, and map task runs, do map is the function that is run to handle a map task. And what it does is it applies the raw map function to all of the keys and values. It does that, and it outputs an array of keys and values. So each map function takes a single key value and outputs a list of key values that are not the same as the input. It's something else. In the word count example, the input key value of a raw map task, I should say of a single instance of using the map function, the pure map function, the input is a key value that has like, the key is the name of the book and the value is the contents of the book. Well, what is output is a list where the key values, the key is a word and the value is the number 1. That was how it works in the word count example. In principle, it doesn't have to be a ready-made list. It could be an iterator, something that sends over one value at a time just to make it faster, so you don't load massive blocks of lists in memory. It just flows, right? That's fine. That's not an important detail. But yeah, basically that's what each mapf does, and each mapf being the map function. The map function is user defined in the sense of MapReduce. The user who's running the MapReduce task specifies mapf, and then domap, it takes mapf as an input to tell it how to handle the map task by applying mapf to all of the input key values. And when it's done with them, it saves them on the same computer that, I should jump back here, local write, it saves the intermediate files onto the same computer where the map task was executed. A single worker computer, so all of these circles represent, all of the ovals, ellipses, represent computers that are running an instance of the software. All of the workers could in principle handle at least more than one map task, that's fine. But the point is, each worker saves its output locally onto its own computer, right? And it saves it into files ready for the reduce. So let's look at the reduce. What the reduce does is it takes as its input, so looking straight at the word count again, which is here. I have to scroll manually because of the lag on Visual Studio. The reduce task takes a key as input. It takes a single key and a list of values. So these are really what it is doing is it's taking key value pairs at the same time for a single key. And the fact that it's a single key is important for the general outline of how this works. So like we said, the map phase, it takes key values and spits out key values. Well, the reduce phase aggregates for each distinct key all the values into a list, and then it processes them into another list of key values. Reduce, for simplicity, typically only outputs one key value per reduce task, but whenever I start to get confused, it pays to think of the word count example, right? So in the context of the word count example, we said that map spits out a word and a value. In terms of the MapReduce task globally, we don't actually care where these are stored or anything. After the map phase is done, we just have in any, like we could imagine it as just being one list that contains all of the key values output by every pure map function applied within every map task to every input file. All of those, just like a big pile of crap. So like the keys are the words, the values are just the number 1, so each value is the same in this particular example. And we just have a massive list of those. And the point of the reduce phase is that it's supposed to aggregate each distinct key, convert the values into, a list of values. So instead of having, let's chuck up Notepad quickly. Instead of having something like key value 1 value 1, key value 2, key 2, value 3, the reduce task prepares its input before processing it into the form key value 1. So this is a list with 2 elements in it, and key 2 is a list with 1 element in it. So it aggregates, it basically bunches up the data based on each key. And that's why it's important, an important part of what we implemented is that it's the map phase worker uses the key of whatever its output. So the map phase is outputting key word value the number 1. It uses the key as a hash to determine which reduce task is going to handle the reduce, and that is necessary because every reduce task has to handle all of the keys all of the key value pairs that have that key as the key, meaning all of the key values that have a particular key have to go to the same reduce task. And that's why if you hash the key, obviously you will always get deterministically the same output, and so our process will always specify the same reduce task, and so it will always get saved into the right place, the file that the reduce task expects. So the map phase workers themselves just arbitrarily spit out keys and values, and so therefore they save them locally on their own computer, with the intention that the reduce phase picks out. Oh, actually, I shouldn't phrase it that way. They save them on their own computer, but by using the hashing, everything that has the same key is saved in the same file for the reduce phase to pick up on. That's why the intermediate files, we have an intermediate file, as it says up here. We have an intermediate file for, this is 2 map tasks and 3 reduce tasks. And we have an intermediate file for every map task and every reduce task, because if ever the same key comes up, it will go to the same reduce task. But if the key has been found in different map tasks, obviously because each map task is saving onto its own computer and they're on separate computers, don't communicate with each other at all, they may end up in different files, as in identified by different map task numbers, but they will always have the same reduce task number because of the hashing. And that is why the reduce task starts by abridging every key that it can find, by checking all of its own reduce task numbers across every map task number. So it has to be able to access all of the computers. And the reduce tasks are running on completely different computers, so it remotely reads from the map task computers using RPC remote procedure call, which we haven't discussed yet. That's for the next bit. Yeah, pretty much. And so in the word count example, the reduce task takes for each key is individually sent into the reduce pure function with its string of values, and what the reduce task does is it adds them up, because all of them have all of the intermediate key values spit out by the map task, spat out by the map task. All of those have value 1 and key whatever, and so when it's abridged, you get that key and the value 1 for every time the word appeared, the key value pair appears. And what reduce does is it just adds them up and spits out, well, it spits out just the value, the way this is implemented, but you can think of that as the key value with the same key and the reduced value. So the key here, for example, is, the word the has values 1, 1, 1, 1, 1, 1, 1, because it appeared 7 times. I did just say 1 7 times. And that will return the same word, the, as the key, and the value will be 7. And that is saved into the output. And so each reduce task saves its own output onto its own. Actually, it doesn't save onto its own computer, but I think that's a bit of a technicality. It saves it into like the global file system, but I don't know what that is, how that works, so I'm just ignoring it. Within the scope of this coursework project, everything uses the local file system because we're not actually distributing shit, so it's fine. And the one thing that I haven't clarified is that the reduced tasks can also handle multiple different keys. So obviously when you're doing the hashing of the map tasks, you have like a crap ton of words coming in the word count example, like we had zigzag, we had like forest, I don't know, we had like thousands of words, and they get hashed to determine which reduced task they're going to, but obviously some things will get hashed to the same thing because there aren't going to be that many reduced tasks, and so the reduced task, by checking all the intermediate files corresponding to itself, will for every key pick up every key value pair that has that as the key, but it will also it won't just pick up a single key, it will pick up a few different keys that happen to get hashed to that reduced task. And so there's no significance among the output files which output file something lands in. It just happens to be which key, it happens to be determined by which key happens to hash to the respective reduced task, or indeed the respective computer that handles the reduced task. I think, yeah, you get one file for each reduced task, and in principle you could just merge them all at the end, but there's no actual point in doing that because, as it said in the paper, you could often run those as the inputs to the next MapReduce task, and then circle of life and thing. So yeah, that is my attempt to explain this shit. We have a nice diagram. I mean, I appreciate my explanation is awful. Definitely not as successful at explaining it like I'm 5, but I'm just trying to get my thoughts together on this. Because it is, I mean, you can sort of see how it can be useful, but without really trying lots of different examples, I don't think just single word count is enough to really get your head around what MapReduce is. But if you have a bunch of examples under your belt, then you can sort of reason with it a lot more easily than I have right now. I mean, I think I have a decent idea, but it's not quite clear enough that I can actually explain it properly. So I gave it a shot now with my 20 minutes of ranting and shit. But yeah, pretty much that's it for now. I'm happy. I'm not going to keep trying to explain it. I'm just going to move on. What I will do is just go through the code we've done so far quickly with a view to explaining what's happened. What's what. So we haven't implemented the entire MapReduce, we've just implemented do map, do reduce, and in the word count example, the map and reduce pure functions. And literally all of these are completely abstract when taken by themselves, but they make perfect sense when you put them all together. Like, it gives you a word count. By word count I mean something like this. So it's a per word count. For each word it tells you how many times it appeared, rather than reducing all of that by adding all those numbers up. It's not the one. So yeah, I'm gonna just go through the code. So let's start at we'll start at the doMap function. So doMap is run for each doMap, an instance of doMap, this function, corresponds to an instance of a map task, which map task this is, and that corresponds to an instance of a file that provides input data in file string. So there's a bunch of code here. There's not actually that much code, so it should be fairly simple to just run through it in about 5-10 minutes. We start by defining a list of encoders for each reduce task. So the point, of course, is that map tasks and reduce tasks are predetermined before we even pass the input into the entire MapReduce paradigm. The number of map tasks and the number of reduce tasks is predetermined. The number of map tasks equals the number of input files. Those correspond to each other, and the number of reduced tasks corresponds to the number of output files. You can see that here, loosely speaking. Not exactly, because this is drawing workers. Workers are just computers, and computers can handle multiple map tasks or reduced tasks. But these arrows coming out, each one of those corresponds to a map task, and each one of these is a reduced task. So depending on how many files you put in to the program, that's how many map tasks you have. The number of reduced tasks you pass in as a number, you choose it yourself, and that is the number of files you get out. So yeah, obviously you don't choose how many files you're going to get out by having the files there in the first place. That defeats the point. Yes. So yeah, the map tasks always have the reduced tasks in mind, of course, because whatever they output has to be prepared to go to the correct reduced task. So the first line of code specifies an encoder, a JSON encoder. It specifies nReduce, the number of reduced tasks, that many, a list of that many JSON encoders. Because JSON is the format we use to transfer data, and so a JSON encoder is going to be something that writes to a file. We're going to, the next part of the code, next line, let's highlight it. The for loop at the top, again, for each nReduce reduced task, each of the nReduce, that's a number, reduced tasks, we create an empty file, and the map task that's running this creates its own empty file, and so the file name is the job name, the map task, and the reduced task, which is R, the dummy variable in the iteration across all the reduced tasks. So this is a quick lambda that outputs a quick, not even a lambda, I guess, because it has a name, but it's a quick function that outputs file names, job name, map task, reduced task. If I run a test, I'm going to quickly run a test to show you what that looks like. I'll explain what I'm doing with the command line. I've sort of changed the way I'm handling that. I'll explain that when I'm done explaining the code so far. What was the test code again? It was like go test run sequential. I think that's it. That should hopefully work. Yeah, so these are the shit, it deleted all the intermediate files. I was going to show you some intermediate files. Well, actually, this is what they look like. These are the file names. No, those are not the file names. Unfortunately, yeah, I've lost the actual. Let me just see if I can, for a second, do a test that outputs some intermediate files so that we can look at them, because those are quite helpful in understanding what's going on. We're going to be doing word count anyway, because that's the motivating example, and that's the one that I've done, so I may as well look at those. We have some. Yeah, what was the name of the script that actually tests? What was the name of the script that tests? Whoops, my bad. CD main. So in the main folder there is a script that tests the full process. It's called testwc. .sh. Okay, let's see if we can pick up some intermediate files. This is what the intermediate files look like. Let me print screen that in case it gets deleted. Okay, sick, it didn't get deleted. So this is what I was saying, sorry about the digression. Job name, hyphen, map task number, hyphen, reduce task number. So in this example we have 7 map tasks and 8 map tasks. 0, it starts counting from 0. 8 map tasks and 3 reduce tasks. So this code, like I said, it starts by making those files. We created the empty file. This map task created a file for each of its corresponding reduced tasks. So say this is map task 1, it will have made all the files that are like job name -1 0, 1, 2, those three are going to be made by this. And we made the encoders, which are the things, abstractly speaking, these are just the things that save to those files in the correct format, which we don't have to worry about because code magic, I don't know. This is what it told me to write down, so I did. But yeah, basically, what this code does, to break it down, it figures out the file name, then it just creates a file, an empty file, in the location that we are working in. I guess I could have put it in a temporary folder if I wanted to make it a bit cleaner, but creates all these files by doing that. Well, all of the files corresponding to this particular map task. So say this is map task 5, it's created these 3 files. Then this is just a bit of boilerplate code that says if there's an error, crash the program. And then this, our empty array of encoders, because these are all just empty JSON encoders, we assign to them an encoder for that particular file. So the rth iteration uses file, which we defined here, and this, because it loops, it refreshes for each iteration of the loop, so it will always assign an encoder. Encoders is, after this phase, is going to contain, for each index, for that reduce task, the thing that was going to save to that reduce, that intermediate file. And it says defer file close, which just means when do map exits, it's going to close the file so there's not a memory leak. So that's setting up the files and the things that write to the files. That's what this thing that's currently visible does. Next part of the code reads the raw files, the input files, which are these. Well, it only reads one file. That's each map task reads only one file, so there's only one in file. This code reads it to input bytes, and then input is converted from input bytes to a string, so it is just the actual content of the file. Why it's input bytes and a string is just Go technicalities, not worth worrying about. Another fake error here. If there's an error, crash the program. The point is, after this bit of code, input now contains the text that we're going to process, and then we run the map pure function on that text. We said with the map pure function in the word count example, the key that gets, each map pure function gets passed a single key value pair. The value is the content input, and the key is in file, which is the name of the input file, whereas I think I said it was the title of the book, but this is just saying it's the name of the input file. Either way, you know, the input files have the title of the book in them pretty much. It says like Being Earnest, Dorian Gray, whatever. Frankenstein. Steiner said. And just a quick distinction, I said input files may in principle contain multiple key values. In this example they don't. Each input file contains a single key value. I think that's just for simplicity. Cool. Right, and then we iterate over. What does this do? It applies mapf. Oh right, sorry, okay, yeah, we applied mapf to the input key value. So let's just click onto main WC to find out what mapf does. Here it is. Lag, crash, hardware acceleration, or whatever. This is it. So it takes a key value pair, which in the case of word count is the file name and contents. That's what I just said. And what this code does, this line literally just splits it into a list of words, the actual words, so it ignores characters. It's just a bunch of technicalities. It splits it according to non-letters, basically. This is the quick function that splits it according to non-letters, and that is what that does. Details do not matter. Then we have output, which is the result. I'm just making an empty list here of key values, and then for every word in the list of words, in output we just chuck in the key value pair that looks like this. So MapReduce.keyValue is the data structure. The key value data structure, and so the key is word, what the word is. So if it's if it's a zigzag, and the value is the number 1. That gets all chucked into a list, and then that list gets sent back. And so mapf yeah, exactly. So it just returns a list of key values, which go into here, the result. So result is now the list of key values. So we've just come back to do map. We're continuing on. And so we iterate over the key values. KV is a dummy variable for a key value in result. Reduce task ID is, don't forget, each key is what determines which reduce task we're going for. Reduce task ID is the ID, so the number from 0 to however many reduced tasks there are, -1 because we're counting from 0. That reduce task ID is determined by hashing the key of KV. So KV's key is hashed, and then it's done modulo nReduce, just so we get an output that makes sense, namely a reduced task ID, a number from 0 to nReduce -1 inclusive. Right, and then once we have that, we chuck it into the respective encoder, which saves it to the respective file as we defined it earlier, and it encodes it. That means it just saves it in JSON in that file. And then the result of that is assigned to error, which is just a Go convention saying whatever, if there is an error, then it returns the error. And so if there is no error, this passes. If it doesn't, it crashes the program. Fine, whatever, details. Okay, that's what the map task does. It has saved all this shit to intermediate files. So now that we're through with the map phase, we have the intermediate files, which look like this. This shit, right? So let's have a bit of a plunder through the intermediate files, just to get an idea for what they are. So we've run do map for each map task, which corresponds to each input file. Okay. How many input files are there? There are 8. There should be 8. These 8 files, and those correspond to map the digit on the left from 0 to 7 inclusive. That's 8 numbers from 0 to 7 inclusive. And so for each of those, we have a number corresponding to the reduce task. So let's have a look. Map task. Let's look at number 2, for example. Frankenstein. This reduce task, kerosene again, coming from, is that the same cunt? No, it's a different cunt. I'm just closing the window temporarily. Literally kerosene. Kerosene is like, it's like diesel, isn't it? That's probably the smell of diesel. I keep calling it kerosene because it literally smells like the inside of a plane when it's taking off. But yeah, just enjoy the NO2 pollution. Cool. So I'm looking at a single reduce task for this map task. The outputs, you know, they all have the formats. The key is a word and the value is the number 1. So here we have so take a look. We have project, Frankenstein, Wollstonecraft, some words that aren't going to turn up that often, but then we have words like no that are going to turn up quite often, but you can immediately see there's another no here. If I control F, I can see that there are 485 no's in, actually no, sorry, that's not matching the whole word. Whole words, yep, this is it. There are 180 no's just in this file. What that means is the input file that we started with, which is whatever map task 2 corresponds to, which is the Frankenstein story. Frankenstein contains 180 no's. I don't know if this is like the full Frankenstein book or whatever, but yeah, whatever this book is in the example, it has 180 no's in it, yeah? But how do I know it's 180 when I've only looked at one of the intermediate files for that particular map task book? Well, because no will always get hashed to the same thing, which will always determine this file. If I look in here, 2, 1, and I search for no, no results. 2, 2, and I search for no. There is a capital N and a capital O, which because we haven't implemented lowercase, uppercase, those are treated as distinct words. So capital no appears here, no is in here, and in here we have title case and lowercase. So lowercase, 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 title case, lowercase, title case, lowercase. Yeah, and so like I said, it's important that all of the no's are kept in the same file, because 0, 1, and 2 determines which of the reduced tasks reads that file, and the reduced task needs access to every no, or every of a given word, every instance, across all the map tasks. So it's going to pick out its reduced task, like 0, 0, 0, whatever. So a reduced task 0 is going to pick out all the files that have 0 in the second number here. But it's going to look at all of the map tasks, so it definitely catches all of the data. Because don't forget, generally speaking, we don't split the input according to like a book or anything that actually has structure. The input is just an arbitrary bunch of files that contain keys and values. The output is going to be the same thing, and that's stored in an arbitrary number of files as well. With no pattern of what's stored where. That's why it has to work like that. So each instance of the word no is contained, and I'll prove that to you by looking at the other 0 files. This file, so story 3, whatever that is, I'm looking at all the no's. It has like piles of no's in the 0 file. The 1 file has absolutely no no's, and the 2 file has 2 capital no's. Right? Let's look at 6. This is the last example. I'm going to do 398 no's, lowercase and title case, no no's in the 1 file, and this just has 2 capital no's. In fact, the capital no's are always the same. If you notice, like you always get no warranty accept and whatever, but I think that's because that message is printed on all the input files. It's the warranty disclaimer or whatever, if I can just dig it up. Where's the warranty disclaimer? It's probably at the bottom. Look at that the length of it. It's basically longer than the book, this warranty disclaimer. Where is it? So somewhere in here there's a capital no, but that doesn't come up in the actual book. Let me just Control F the capital no. So I have to match case. Yeah, here it is. You see no, remedy, negligence, warranty, all that shit. Right. So that's it. And let's just flick through the reduce task quickly as well. So reduce task is stored in common reduce. A single reduce task corresponds to a single output file. So again, we have that correspondence there between these two things. We have nmap as the input because that tells us how many intermediate files we're looking for. And we have the reduce function, the pure function as well. So let's have a look at how this is implemented. This is slightly longer because there was more jumping through hoops, I remember. Okay, we begin with input array, which is a list of key values, just a list of key values for the time being. And now we are going to put stuff in input array by doing the following. So this loops over all of the map tasks. So M is the map task ID. So don't forget, common reduce, do reduce, which is the function that we're currently looking at, runs for a given reduce task, right? And so a fixed reduce task, we loop over all the map tasks. This tells us the file names we're looking for. Fixed reduce task, M is the dummy variable of the map task. Job name is a single constant for the entire MapReduce procedure. Again, it reads the file specified by the file name we just figured out here. So it reads the intermediate file for map task M, the fixed reduce task, into input bytes, and then it converts it into a string and drops the error. Same thing we did last time. This is an arbitrary line of code that I had to make just to get it to work. Reader Um, yeah, it converts the text in input. Um, so input by the way, we just read the intermediate file. So input is literally just the content of the intermediate file. We convert that into another format here, doesn't matter what, and then we define a decoder, a JSON decoder for the reader. And what the JSON decoder is going to do is it's going to, if we iterate over it, every time we run decode, it's going to pull out the next key value pair and convert it into an actual key value structure. And that's what this does. For, with curly braces, is an infinite loop. So we define an empty key value. Key value is actually going to be the location we are decoding to. So dec.decode automatically, every time it's run, pulls out the next line out of the intermediate file, which we've labeled by loading its data into the decoder. And it assigns it to kv, and it keeps doing that. It keeps doing that until there's an error. So if there is no error, then it runs this bit of code, because this is saying if error is not non-existent. So if there is an error, if there is no error, input array gets this appends kv to the input array, and kv, as we said, we just wrote the thing from the input file into it. And when it's done, it just breaks, which means it moves on out of the infinite loop and continues on its merry way. So yeah, at the end of this input array will now contain all of the keys and values that correspond literally across all of the intermediate files that we had here that correspond to that reduce task. All of them. So if this is reduce task 1, literally everything that is in here, and in here, and in here, and in here, and all the way up to the end, all the things that end in 1, all of those are now present in key value format, so in the correct type, in the list that is called input array. That's when we get to the end of this infinite. I'm reading map again like a dumbass. Sorry. When we get to the end of this infinite loop. That's step 1. Next, we sort it according to key. So key. This is an alphabetical comparison of words. This is the key of the ith entry in the list of keys and values, which we called input array, and it uses that in order to, I think this is an in-place sort, to sort those, so that when we're done at the end of this, we have the same list of all the keys and values, except they are sorted alphabetically according to key, which means, well, what do you think it means? Except, obviously, all the duplicate keys that correspond to different values are next to each other. That's why we care. Otherwise, we would not give a shit about sorting it. We care because after we've done the sort, we have the same thing, except in the order in the list, that all the keys that are the same are next to each other. And then we run this. First of all, there's a bit of code here that just sets up the files that it's going to get output to. So again, reduce task outputs to a single file. So here it is. File, create file at the file address given in the function by outFile. If there's an error, drop it. Close the file at the end of the function when the function finishes, and then define an encoder, another encoder, that just adds things to the file. So every time we call enc.encode, it's going to add that piece of result to the final output. And this is where we do that. So we loop across the input array. We have a couple of dynamic programming type variables here. The previous key, which is intended to, because we are looping one step at a time across the key value array, previous key is intended to always store the key that came before. Always store the key that came before. That rhymes. Value buffer is intended to store as we are building it, because what we need to happen is that before we pass the result into the reduce pure function, it needs to be converted to not be in the format where you have duplicate keys with different values. Instead, we want a single key with a list of all the values. So that value buffer is what we're going to use to build that. It's a temporary store of all of the things in the buffer. Sorry, of all of the values corresponding to that key. And so this is how the loop works. We decide, well, there are two cases. One of them is this case, which says that if the key, the current key differs from the previous key, but also we are not at the very first step. If both of those things are true, then what this is going to do is it's going to make a new result that takes the current. Basically, it's going to make a key value of the sort that we want it to be. Well, how should I explain this? If those two conditions hold, so if the key has changed, as we're stepping through the key value array, if the key has changed, then we're going to take everything that we have in value buffer for the previous key, and we're going to send it into the reduce function, and whatever is output by that is stored in the format that key and the output of the reduce, which is of type value in the sense of reducing. That is the result of running the reduce on that key. Then it is saved in the file by encode, and value buffer is emptied. It is set to an empty array of strings, an empty list of strings. So yeah, the point of the whole do reduce is that it should reduce. It should take this. We were at input array, which was just a list of keys and values. It should take all of the keys. For a given key, it should take all the values, put them in a list, and then send it off into the reduce f, which is the function that does the reduce, and then whatever's output by that is stored in the format key. The output value, that key value, is then sent into the final file, and the buffer is emptied. And in practice, because we are traversing a list that has, if I do this, I'm doing it the wrong way, am I not? If we traverse the list, and the list is ordered by key, then all the keys that are the same come up in the same position. This is why when the key position splits, that is our cue to say we have picked up everything. Sorry, when what the key is changes. That means that for what the key was before, we have picked up every value for that key. We've been through all of them because they're sorted. And all of those have been loaded into the value buffer in principle. And so that's why we can say, okay, we're done. That key has that value buffer. We reduce it and then save it to the output. Regardless of whether or not that happens, value buffer is always going to get the value appended to it, the current value, and the previous key is set to the current key for the next, in time for the next iteration of the loop. And so it's important for the flush to not happen when I is 0, which is to say at the very beginning. We don't want the flush to happen because then previous key is undefined. It doesn't make sense to flush. Technically speaking, this actually sets previous key to the empty string, but if the empty string is being used in the app, so if there is a key that happens to have the empty string, then that would fuck up, because previous key being empty string, if the previous key happened to change, so if the first key were not the empty string, it would flush the empty string with nothing. But that would happen anyway. But if it were the empty string, it would, I think, work correctly. I'm not sure. Doesn't matter. Basically, just to avoid this works. I should say, I'm not with an algorithm like this, I'm not always statically happy that it works. Like I can't just look at it and analyze with my hands and go like, oh, this definitely works. Like this has been through testing, right? That's why I know it works. This is the Chomsky way of doing things, and we're not proving shit anymore. That was when I was at uni. bund it, dropped it out. Cool. So yeah, pretty much at every step we just add to the value buffer, and if there is a change in what the key is, that means we're done with that key. We flush the value buffer, and then we have the key, so we can reduce it and whatever and move on. And this just makes sure that the previous key is always set to the correct thing, because it sets it to the actual key, the current key, but then it immediately hits the next loop, so it becomes the previous key. So that's why this makes sense. This last line, I mean. Yeah, that's it. So reduce f is run. I didn't quite say what reduce f does, but I mean I can cover that in like a second. So in the word count example, again, what the input is at this stage is a single word followed by for every instance the word has come up, the number 1 was present in a key value in the input array. And so by doing this abridging, what the input actually is that word and a list of ones. And the number of ones in the list is the number of that word's 1 keys that was an input array, which, following the argument all the way back to the beginning, is actually the number of words in all the books that are that particular word, as in the number of times that word has come up in all the books. So yeah, with that in mind, what does reduce actually do? This. Let me just scroll down. Yeah, this bit of code here. So result is our counter, or actually it's like a sum instance of the counter. It's our partial sum. We iterate over all the values that got passed in. All of them are 1, but that doesn't matter, because we convert them. This bit of code converts the value from string format to number format, drops the error if there is one, adds the number to the result, and then when it's done, converts the result back to a string and then returns it. i.e., it adds up everything in the list. In Python, this is one line of code, but this is a bit of a bullshit language. Like I said, when it comes to prototyping, this is a bullshit language because you have to monitor types, right? I had to convert from string to number to string, and converting to string is non-trivial because there isn't even a parse int. Like, it's a bit of a messed up language, to be honest. I had to handle a potential error from converting a number into a string, which is just like absolute nonsense. So it does that, and then it saves it like we said, and that is literally it, isn't it? Common reduce is then finished. Well, there is also these 2 lines of code which are identical to these 2 lines, and they just make sure that this actually gets run at the end, which I probably could have programmed it a bit better so that this happens. Basically, by switching these 2 around, that might have actually I might not have had to have this condition there, and this would have happened. There would have been less code duplication, possibly. There's no guarantee that would have worked, but it would have made the code a bit nicer. But because I'm not interested in making the code all pretty and optimized and shit, I'm just gonna ignore that, and that's it. So that's that. We're on. Well, it took a whole hour. But nonetheless, I've completely summarized what's happened, and I have a pretty clear understanding of it as well at this point. So I think it was worth it. Worth it to just take stock, and say, okay, I've actually learned something, rather than just what we did previously, very vaguely hack our way with partial understanding. I managed to get it to work with partial understanding, but it's always good if you're going to actually learn the shit to just slow down and kick it out as you go. Yeah, again, just repetition as well. So I'm happy to have finished that. So I'm going to close all this shit, take a bit of a break. Yeah, I'm also feeling a bit happier about the stream of consciousness. I'm feeling a bit more into just actually speaking what's on my mind. So even though my explanations are not great, because I barely have no experience with this stuff, barely understand it, I still think I've done a reasonably good job. of getting everything to work, even as an explanation. So yeah, precisely an hour in now. Yeah, I'd like to take a break, like a classic break, to just play some video games for like 5-10 minutes before moving on. But I mean, even though I suggested doing that in the first stream, it turned out if I wanted to play like Super Metroid or Super Mario Bros, I'd have to use the keyboard because there are no more USB ports to plug in the gamepads. I don't have it in my room at the moment, but like I have a PC replica SNES pad, which is what I've been using for Super Metroid. It works fairly well. Super Mario Bros. Just because particularly if you're speed running it, you're always holding down dash. Even if you're just casually playing it, you're always holding down dash, and so like it kind of sucks. For me, it's so uncomfortable compared to the keyboard where you just go Z and then X every time you need to jump. On a gamepad, you have to I don't even know how people do it. Like hold A and B at the same time. Well, actually, it's not even that. Hold B, always, almost always. Drop it at very particular moments if you're doing a speed run of SMB. But like, you hold B and then you keep tapping A, but you can't just tap A because you're holding B with the thumb. You have to like rotate onto it, or like do this, which I was kind of experimenting with. So yeah, maybe I should just do Super Mario Bros. Using the Dell. The trouble with the Dell is the fucking keyboard is the arrow buttons on the keyboard are absolutely tiny. So I don't know. I'll make my mind up. The fan is actually running on the laptop, but it's pretty damn quiet, I have to say. I can barely hear it. It's not really overheating, even though it's streaming a bunch. I'm impressed. Like it's streaming with barely any CPU usage. GPU obviously still quite heavy, but if you look at that, it's constantly only about 10% CPU to do a stream. I think that might be because I dropped the bitrate quite low. It's on 4000, 1080p, 60 frames per second, but it's on 4000 kilobits per second, which is on the lower end, I think, for that kind of thing, and so it's quite happily being handled, I guess, by the computer. And this is about 8% being used on the webcam app, so those add up to about 20% idle, which is great. I love that. Well, 66% GPU, just because the encoding is mostly GPU. Yeah, I don't know, maybe I should just fancy a little bit of a break, but I guess what's a good way of taking a break? What happens after this? Oh yeah, I guess I should just mention a few things that I've changed and done. So what I said about MapReduce, all that explanation, that comes from half an hour of reading the actual paper. So I mentioned that at the beginning, and this diagram comes from that. This is the original paper. I read it up to and including the end of section 3, so I have a decent idea of what it is now. But yeah, I spent half an hour on that, which is, I think, reasonable, to just get your head around something. If I'd read it before doing the practical, I would have understood it worse. So I'm really quite happy with this way of doing things. I quite enjoy it. Yeah, pretty much. So I did that, and what else did I do since the last stream? Because I took the session off, of course. Not that I'm always going to do work, even if I take time off. I might just chill, and I'm going to start Undertale. It's going to happen. It's going to happen soon. TM. Yeah, I tried to get Visual Studio Code to work better. So for starters, all those errors have disappeared because, well, I went through MIT source code and implemented the changes that Visual Studio Code suggested. So all those warnings are now gone. And the errors could not find package. I fixed those by adding in a .env file that sets the go path to the correct place, because that's why it said like cannot find package at go path, and then it printed like, you know, audaciously printed the wrong go path. Like, fuck you. I mean, I you know, even if like in the console I tell it to set the go path, it just doesn't do it unless I do this. Apparently, this is what makes it work. So, fuck knows. Like I tried also changing this to the correct go path. The debug settings also now have a go path in them, but that did nothing. Did absolutely nothing. So, .env fixed it. Another thing, apologies last stream for always loading the console. It sort of overlapped with the camera section, so I noticed when watching the stream back I couldn't actually see the fact that the tests passed. So now, well, A, I'm going to stop doing that, so again, if I'm on the right of the Cortana box, I'm safe. But also B, I managed to get the terminal here to work in Bash by clicking something, I can't remember what. PowerShell's gone somehow. But yeah, having a Bash terminal means I can literally do everything in the terminal in Visual Studio Code. It still lags, unfortunately, because I'm going to see if I can fix that as well, but just as a general point, I can now do shit in the terminal. It's all good. What else did I fix? There isn't much that I did fix, to be honest. I deleted some temporary files. Schedule got modified. What did I change in schedule? Oh yeah, it was one of the things that was warned about. Yeah, no, that's literally it. Nothing else really was changed, I don't think. Oh yeah, I renamed this to something that makes it slightly shorter. So even though I have like .env saying what the go path should be, I also have to run it here at the beginning of each session, because it doesn't. Here it is. Else it doesn't work, because it's just not user friendly. It's like, you know, people don't standardize, I don't know, the documentation is not really legible to a newcomer like me, but it's fine, everything's working fine. Yeah, I still don't want to move on to the next section. Should I just cut the stream short? Probably not, because I would actually like to see if I can push out part 3 and part 4 as well within 72 hours. I said I'd like to finish everything within 72 hours when I started MapReduce. If I push myself, I can do that, I think. So I'm contemplating it. But I guess I've taken enough of a break now. I'll tell you what, I might just get up and stretch myself for a minute. So I'll just say, don't know if anyone's watching. Like I said to myself, I'm not going to check, but I'm just going to sort of what am I going to do? I need a better way of communicating, to be able to just print overlays of text that say something like back in 1 minute or whatever. I'll just say, you know, back in 2 mins, put it there. And literally I'm just going to use those 2 mins to get up, and nothing else, because like my ass is getting fucking numb as hell. It's getting really bad now, so I'm looking forward to finishing MapReduce, just so I can be like, what was I going to say? Well, just take a break for like 3 or 4 days, you know. All good, all good. Wow. Oh shit, look at that. SNES controller is actually here. This is the SNES controller. Buffalo classic USB gamepad. out of tune. Yeah, okay. Yeah, I gotta do, what was the, am I even on camera now? Let's chuck up the camera, yeah, I'm on camera. Gotta do, part 3, scheduling. Do that now, I'll probably spend another hour and then just cut the stream off. Might go further if I feel I'm really close to the end, but yeah, I honestly wish, like, I used to play the guitar regularly, but now guitar's just busted. Strings are really old, everything's out of tune, it goes out of tune, you know. If you say like, oh, the strings are out of tune, that means they're bent to the point that if you tune them, you don't get consistent pitch going up the fretboard. And it sounds terrible, and my technique is awful as well now. Unfortunately, sort of moved on to the piano, generally speaking. Yeah, okay. Classic bit of neo soul, The Lung by Hiatus Coyote. I think when they come to London next time, there's going to be an absolutely massive hype. I think the last time they were in London was 2016. Band that pretty much everyone who listens to modern music likes. It's just a universal thing, really quite amazing how it's just kind of going beyond genre, going beyond taste. It's just objectively good music. Objectively good music. Yes, there is such a thing. Cool. Okay, microphone, lights, camera, action, ready to go on to part 3. I'll leave the paper up, just because the paper seems to have been useful so far. Let's do, before I set off, let's do a quick sync test. Yeah, syncing is just perfect now. The visual syncing, the audio syncing oscillates, unfortunately, so sometimes it messes up slightly, but I think I have it mostly down, to be honest. Yeah, okay, now I have to bring myself to start the next bit. Ooh, okay, cool. Well, actually, I'm gonna blow my nose first. Just a sec, guys. Control 0 is I have some water here. It's really old. I filled it on day 1 of streaming, Saturday, but I can't be bothered to go get new water. I think it's probably okay. Check this out, 41 dropped frames. I almost never get dropped frames, which shows that I'm using reasonable streaming settings, I think. I think dropped frames is how fast the CPU can encode stuff. Or maybe it's how fast it can actually deliver them to Twitch. I'm not 100%. I'm not even 50%. I have no idea. But yeah, here it is, 4,000 kilobits per second, 4 megabits per second, which is half a megabyte per second. Yeah, okay. Let's get to work, that's enough slacking. I'm happy I've done all this right, I'm not going to check again, I'm just going to continue on to part 3. How long is part 3? Not that long, in terms of the text, but then yeah, it's also reading all the comments in it. Well. Witness the fitness. Oh shit. The Crawfordson liveth, one hope, one quest. Man's been Stockwell now. I have a friend who lives in Clapham, so I pass through Stockwell which is where roots maneuver is from. It's a really, really awful area, by the way. Don't recommend it. I mean, I took a nice photo, but it was nice just artistically rather than aesthetically. It was really awful aesthetically, just like wouldn't want to live there. But yeah, I'm counting my blessings that this is a nice Java state. Okay, 2222 is the time. Let's go. Your current implementation runs the map and reduce tasks one at a time. Indeed, well, obviously the biggest selling point is that it automatically parallelizes ordinary sequential code without any extra work by the developer. So yeah, just to be clear, what we're doing is making a developer platform. Other developers can send in their customized map and reduce tasks, and this will run it for them, and the custom input files as well, and it will run it for them. That is literally the same as when I made the sort of modular Pokemon Go bot, Abio. You can check that on my GitHub. I'll just chuck it up very briefly. github.com/pirate/Abio. You know the way this works. If I just look at the README here. You know, each agent object, agents handle somebody's filtering requests for Pokemon spawns coming out of the Pokemon Go map. And each one comes from a script file, and that's a completely custom file. It has a dictionary, which is like a list of key values of channels to post to, Discord channels to post to. And they have handles, you know, these identifiers. And there is a filter function, takes a Pokemon and returns, this is a pure function, the filter, takes a Pokemon and it returns the channel handle for where it should be sent. And so, in principle, if we have any other developers or anyone who wants to do it themselves, they can just write their own agent. And that gets integrated into the bot, and it does its thing. You know, it's just the same way you can write your own map and reduce functions and input data for MapReduce to be run on, like, whoever's running it, Google servers or like Hadoop, or I can't remember the other actual MapReduce things out in the wild. But yeah, pretty much it's quite similar to how this works in that sense. Abio and the other version of it, those are my two best projects so far. They taught me all that I know about Node, and honestly I know quite a bit about Node now. Not some of the more advanced stuff, because I haven't had to use it. I don't really know how to mess with streams, parallelization, that stuff I'm not that familiar with, but like basic web development ideas I'm completely down with them now because of that project. Just saying, you know, hire me and shit. In this part of the lab, you will complete a version of MapReduce that splits the work over a set of worker threads, which, you know, run in parallel on multiple cores, not distributed across multiple machines as in real versions. Nonetheless, they will run in parallel for starters, so we'll definitely see a performance improvement. And your implementation will use RPC, so it will actually use RPC to simulate distributed shit, just like an RPC from a computer to itself, just as a simulation. Let me open the window again. I'm getting short of breath again. Whoa! How do I always forget how I open this window efficiently. It's like some hectic procedure that changes every time I do it. The code in MapReduce master go, yeah, as soon as I open the window, the laptop fan turns off because its temperature just drops, you know. Drop the temperature. Okay, master.go does most of the work of managing a MapReduce job, and you know, we're not editing that, unfortunately. I may or may not read through that code at a later date, If I do, I may or may not do it on stream, I'm not sure yet. But for the time being, I'm not gonna. I'm just, what we know is what we know, and we can build this up later on by, first of all, finishing the project, and after that, perhaps taking a deeper look at the source code, or moving on to the next project. We also supply you with the complete code for a worker thread in Worker, as well as some code to deal with RPC in Common RPC. Your job is to implement schedule. Let's have a quick look at schedule off the beginning, off the cuff. Shout out to Off the Cuff in Herne Hill. It's a really sick name for a bar, and it's actually turned into, a music venue that actually puts on stuff that I'd like to see. If I lived in South London, I would be down in Off the Cuff. Been there once so far to see a band from Churchill, from my university. It was good. They should do it again. They're not going to be watching though. Where is schedule again? It's in the MapReduce directory, isn't it? It's here. So I've already edited it just because it told me to get rid of the underscore here. Literally, it just told me to get rid of the fucking underscore. So I replaced it with camel case. Yeah, so, sorry, what do I mean? Underscore is this, camel case. Yeah. Naming conventions. Not even word conventions, just symbol conventions. Okay, so, yep, schedule is already mostly in place, and it's literally the only function in this file, so, okay, that's good. It's nice and simple. And then this is going to say what schedule does, so we're going to read it. Let's read it here first. The master calls schedule twice during a MapReduce job, once for the map phase and once for the reduce phase. Don't know what that clicking is, it sounds like a ping pong ball. Schedule's job is to hand out tasks to the available workers. Workers, of course, handling both map and reduce, as in not simultaneously, but handling either map or reduce. There will usually be more tasks than worker threads available, so schedule must give each worker a sequence of tasks one at a time. Okay, so they don't buffer tasks, fine. Buffer, of course, in this sense, what I'm thinking is it could be that the worker gets sent tasks and then it holds on to them before executing them. So it's in the middle of task like 14, it gets sent task 26, so it just has 26, as in it's going to do that after 14. Loads of workers, loads of tasks in different places. There will usually be more tasks than worker threads. Yep. So it gives schedule must give each worker a sequence of tasks one at a time. So that could be thought of as a Go channel. Works in a similar way. You can buffer channels in Go. You don't need to. You have a choice. Schedule should wait until all tasks have completed and then return. Yeah, I'm feeling channels are coming up. Go channels. Because so far the code that we've done is completely synchronous, no concurrency at all. So it's going to be fun to actually use Go's concurrent features, like the channels, which I'm going to talk about when we get onto them. Schedule learns about the set of workers by reading its register chan arguments. So this is a channel through which workers, I'm guessing, send ready messages. That channel yields a string for each worker, yield meaning receives on the side of schedule, containing the worker's RPC address. So RPC is a protocol. It deals with addresses like most protocols. IP is a protocol, internet protocol, IP addresses are a thing. Some workers may exist before schedule is called, and some may start while schedule is running. In either case, all will come through on register chan. I'm guessing register chan is separate from schedule, then it's not defined in schedule, or else this would not be true, this sentence here. All will appear on register chan, given some workers exist before schedule is called. You want the workers, realistically, to send messages as soon as they are created, and so if schedule is called after that, it should be able to receive these messages, so the channel probably exists outside schedule. Schedule should use all the workers, including ones that appear after it starts. Which is, yeah, just another way of saying that. I guess the test is going to test that. I hope it does. I don't want to rely on myself implementing that correctly in a language I know nothing about. Schedule tells a worker to execute a task by sending... Here... Wait, how much more of this is there? Not that much, okay. Doggo outside. Warf. Warf. I can hear the panting. Oh, there it is. Black-eyed dog. Black-eyed dog, hear my name. Fun fact, I found out about that song by Nick Drake on the day Margaret Thatcher died. Highly tenuous. I think Black Dog is something Churchill famously said, and then Thatcher died on the day I heard the song Black-Eyed Dog. Hella tenuous link, but yeah, it's like, as in a really, really weak coincidence. Yeah, use the call function. No, I'm reading here. Schedule tells a worker to execute a task by sending a worker.doTask RPC, remote procedure call, to the worker. So, yeah, schedule sends the task to the worker. The arguments are defined by doTask args in common rpc.go. The file element is only used by map tasks and is the name of the file to read. Schedule can find these file names in map files. Obviously this makes no sense in isolation. We're going to have to get our hands dirty to figure out what it's actually talking about. Use the call function in MapReduce common rpc.go to send an RPC to a worker. The first argument is the worker's address, the worker's address, as read from register chan. Second argument should be worker.doTask, as in that string is the second argument. The third argument should be the doTask args structure, which is arguments. So it's passing the command. Well, I guess, remote procedure call calls functions on different computers. So workers will be running worker.go, and so presumably this has a doTask function. Here it is. Okay. So what this is saying is run doTask. When it says worker.doTask, that means this is the function we are calling. The third argument is the arguments, which is some sort of structure that is accepted by here. So, it has arg, doTask args. So arg is the name, this is the type, as in it has type argument. It has a bespoke type, like the type is literally whatever this needs as arguments. And it has something else, which is a pointer to fuck knows what. I think this is an optional argument, I'm not 100% why that is there. And it returns an error. Yeah, it's that convention I was talking about again. If something returns an error, in this sense what that means is it returns an error object, and if that is nil, it means there is no error. Fine, or whatever. And this line means that this is a method that workers exhibit. As in WK is the name of the worker. It's the dummy variable representing the worker that has this as a method. Basically, this is what that means. It's a way of doing object-oriented programming. You're saying like, okay, the worker has a doTask method and this is how I specify it. Writing down a function and saying anything that any worker object is allowed to access that function for itself, and WK is this. In most programming languages this would be this. This, as in the thing I've highlighted, would be represented by the keyword this. This is, I think, a bit nicer actually. I prefer this way of doing object-oriented, to be perfectly honest. I think it's nicer. it's a bit more functional. It's a bit more like I'm matching bits of code up to other bits of code without subordinating any of them, if you see what I mean. So it's not that I'm defining the object and then I'm saying, oh, these are the methods. Instead, I have methods and I have objects and I connect them up to each other. And I have, I don't have one nested within the other. I think that's cool. I like that. It's one thing that's nice about Go. 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 That British accent. Sometimes it goes really go. Like, I had an English teacher, shout out Mr. Merchant, in year 11 who had that exaggerated. Okay, children, listening please. Cool guy. Indian ethnically. Don't know where he learned to speak English. Never asked. I should have asked, I wasn't so worldly back then, I guess. Like, keen to know such stuff, Yep. What else is going in the RPC? So call, I guess, is like the RPC method. It does RPC stuff. It does an RPC call. It's like what this entire file culminates to. First argument is the address. Second argument is the channel. Sorry, is the function to be run with worker specifying what file it is. So if the worker's address is actually the master, then this will probably throw an error because master doesn't expose worker methods, I guess. If you think of it as a method, I guess it is kind of like a method. It's a method within a file rather than a method within an object. Fine. Method, like I say, is tying a function to a thing rather than function by itself, which is the more kind of piece of a puzzle attitude towards functions. It's not subordinate, it's on the same level conceptually. I just wanted to test my microphone. Sometimes I feel like it goes off a bit, but it looks okay. Maybe I should boost it slightly, but for the most part I think my speaking is fairly clear. It would be better if I had a headset, I know that, because the microphone is all the way down. You can actually just see it on the camera right now. There. But I think, yeah, this is okay. I can always just turn it up. So I want to quickly take a look at what call looks like, just to get an idea of what an RPC looks like from the inside. Master RPC has a call method. It also has a shutdown method, a start server method. This is stuff we're probably not messing with. Stop server. Where is call? Do I have to implement call? Surely not. Nah, that would be dodgy if I had to implement call. It doesn't seem to be there. Oh, I'm looking in master RPC instead of common RPC. Common, of course, meaning everything should be able to access this stuff. Let's have a look at do tasks args first. So this is the arguments structure that we were talking about, the bespoke argument structure. It has a job name, a file. In the case of map, the input file goes here, otherwise I guess reduce is just getting nil assigned to it. Phase, are we in map phase or reduce phase? This has type job phase. I do not know why this could not have just been a string, and it shouldn't have been called phase, surely. Why not? I mean, map phase, reduce phase, okay. Task number is the task's index in the current phase. How many tasks? Yeah. That's nmap and reduce. Those are the number of possible task numbers for map and reduce respectively. That checks out completely. What else is there? Num other phase. What the total number of tasks in other phase. Mappers need this to compute the number of output bins, as in reduce bins. Reducers need this to know how many input files to collect. Okay, understood. Yeah, other phase, yeah. So in the case of reduce, this is the number of map phases. This is nmap. And in the case of map, this is nReduce. Cool. It has an args interface. This is lazy coding. Why doesn't it say instead of interface? Why doesn't it just say args and then type do task args? Don't know. It doesn't matter. This is quite minor stuff. Func call SRV. SRV is what was call again? First argument we said was supposed to be the address. Please don't change this function yet. Indeed, it doesn't want me to mess with. It has a fucking dial, Unix, fuck knows, details. It's just abstracting it all away and saying, you know, don't mess with this function. Does it say what call does? It does, but that is a lot of details. I will read that later. Yeah, I guess I might have to cut this stream short without starting to implement anything, just because there are a lot of details to get through before starting. Never mind, it's fine. Yeah, I moved the microphone in slightly closer. I think this is a bit better. On the camera, that's just like, is that visible? Nah. Mate. Clear. Yeah, this doesn't seem to correspond to what I... Oh yeah, no, it does. This is the address. This is the function we're running, RPC name. SRV is the address. Args is the arguments for that function. And this is what we said we're supposed to set to nil something about a reply, I don't know. Let's have a look. Call sends an RPC to the RPC name handler, i.e. the function, on server SRV, i.e. the address of the server, with so by server, you know, the word, I was using the word computer. Server is an individual computer that runs a worker or a master or the user interface or anything else. So a single program instance is going to be SRV, particularly because we're only doing things on this one computer. SRV actually means, like, virtually speaking, we're simulating different computers, distributed systems, of course, simulating that by having all these different servers with the different addresses. SRV. Argument args waits for the reply. Okay, so yeah, it sends the RPC, waits for the reply. So I guess it blocks. It should block, I think. In Go, it's good for things to block because you can easily compartmentalize them in separate threads. So blocking is good. Makes things simpler, and leaves the reply in reply, which is what? Oh, so in reply we pass in a pointer to where we want to store the reply, I guess. When it says put nil in reply, that just means drop the reply. Call returns true. Okay, it returns something. It returns true if the server responded, and false if it didn't. Replies, yeah, if call received no reply from the server. Replies contents are valid if and only if call returned true. Well, yeah, obviously. I think otherwise it just doesn't bother to overwrite. That's how I would implement that. So, you know, whatever it said it would reply into, if call returned false, it just doesn't edit it. So even if it already had something in it, it's not valid. You should assume that call will time out and return false after a while if it doesn't get a reply from the server. Yes, that's how it's supposed to be done. Please use call to send all RPCs. Okay. Please don't change this function. Okay, yeah, no, that's fine. I know what call does now. I'm quite comfortable with that. It's just teaching you to use something. This bit of text, these comments. Okay, cool. So now we know about call. That's this. This is all about call. Your solution to part 3 should only involve modifications to schedule. If you modify other files, please restore them for the actual test. Use go test, run test parallel to test your solution. 2 tests, basic and check. Oh, it actually says what the tests are here. Should have checked that earlier, I guess, for part 1. Camera. Get it flat. The latter verifies that your scheduler causes workers to execute tasks in parallel. Nice. RPC package documents the Go RPC package. Golang package net/RPC is the name of the package. Schedule should send RPCs to the workers in parallel so that workers can work on tasks concurrently. Well, yeah, it should not wait for the tasks to come back and then send the next RPC, obviously. You'll find the Go statement useful for this purpose. See concurrency in Go. Alright, check it out. We're going to be using concurrency. Yeah. Schedule must wait for a worker to finish before it can give it another task. Yeah, but it can give other tasks to other workers. You may find Go's channels useful. Yeah, so a channel for each worker makes sense within the scheduler, so that it awaits. Like I said, channels should individually block, but if you want something to not block, you just start another channel. Not a channel, sorry, a coroutine, that's what I mean. A coroutine. The word Go starts coroutines. In Go, these are called Go routines. Yeah, that's fine. Again, you may find. Oh, it says here you may find the channels useful. Ah, true. Yeah, actually, you don't need. You can just use channels instead of coroutines to do that. As in, yeah, you make a channel to represent each worker. Those are even lighter weight than coroutines, and then the channel receives messages like, "Oh, is it ready to go?" And if you iterate over a channel, what it does is it blocks until the channel comes back. Yeah, you want to use the channel and a Go routine in parallel. Sorry, in tandem, as in pair them up and use them simultaneously. So the Go routine will be it'll be iterating over the channel and awaiting things from the channel and not doing anything else, but that's running in parallel to the main thread, so it doesn't block the whole program, it just blocks the routine that it's designed to wait for stuff. It's quite a neat way to do concurrency, I think. You may find sync.wait group useful. Sync.wait group I know because there was that fucked up problem within a tour of Go, the last question on concurrency that was just like required you to use shit that you don't know about because it didn't tell you about it. Well, a neat way of doing it is sync.wait group. Sync.wait group awaits various things at the same time, and then when all of these tasks are completed, it will continue. I think that's the idea of this, if I recall correctly. So in JavaScript, this would be promise.all. Which I've never actually had to use, but I vaguely know about it. So it's kind of, you think about all these things happening at the same time, what this does is it waits for all of them, the whole group, to come through, finished, and when they're all finished it moves on. So it's like a proper parallelization method. If you imagine like, oh, I have 3 pens representing different shit and stuff's travelling up the pens at different paces. Well, my sync wait group is this piece of paper at the top, and when each pen, like, I don't know, whatever it is, has travelled to the end of each pen and made the mark, when all the marks are there, this continues and does the next thing. Yeah, so that's the idea of promise.all in Node and wait group. Promises are actually in vanilla JavaScript now as well, which is cool. You can do them in the browser, in the client. And yeah, sync wait group does the same thing. I think I haven't used it yet, so we'll have to figure that out. The easiest way to track down bugs is to insert print statements. Yeah, of course. Perhaps calling debug in common.go. I don't know what that does. Let's have a quick look. Debug will only print if debug enabled is true. Yeah, but if I have debug enabled to true, then it will print all that shit, the 100,000 numbers, is what happened last time, so I think I'm going to leave it to false. I'm not sure I trust it anymore after what happened last time. So this is just a way of having, basically it's a way of printing statements but having those statements disappear if you turn debug off. So it's just to help you, the developer, and then at the end, if you're finished with your program, you can Control F to delete all of the debug stuff. So maybe I should just make a new debug constant, and to get this to work I change it so it depends on a different constant, because this will print a bunch of other shit. But then again, maybe the word debug is what's causing all the unnecessary printing. Maybe if I Control F I will find it. Okay, I'll spend a minute doing that just because I'm curious. Control Shift F, find in all files, debug, open bracket, go. Yeah, so it already debugs, like it does bare debugging. Yeah, so this is the shit that we were seeing, if you remember. It prints every map statement, every reduce statement. But I mean, do I go through all this and comment out all this code so that I can debug what I want to debug? To be honest, yeah, I think that's what I'm going to do. I think that's what I'm going to do. So, you know, delete every map, delete every reduce. Now at least I know how to do that. If you remember last stream, I was puzzling hard, trying to figure out where all these like numbers and shit were coming from, where all the print statements were coming from. But now I know. Now we know. Now we know. Now we know. Yeah, I should get back onto watching comedy, shouldn't I? Yeah, it's always good. It's always, you know, it always improves your motivation, your outlook on life. Comedy's good, mate. In case you didn't know. Well, everyone knows it's good, but people will forget to do it. Yep. I wonder why the word the return is even there. It does nothing. One line of code effectively was what this is, but the fucking linting thing, the lint meaning, I think lint is something that enforces conventions in programming style. So if I save while the linter is enabled, it'll just undo my single lining, because it's like, fuck you, that's bad convention, don't single line. But I don't really agree with that. I think if you have like an atomic thought, then it's fair enough to keep it in single line, in my opinion. Like that print error stuff, if you remember the print error stuff. It's like, if error not equal to nil, panic error, that stuff. Should definitely only be one line, but it's a small thing, I'm not that bothered. It's not that deep. Yeah, insert print statements, perhaps by calling debug. Okay, cool. Collect the output in a file with go test run test parallel going to out. Okay, yeah, this is if I guess this is intended for if things can't fit in the console, just send it into the file. Why wasn't this in the very first bit? Because then it wouldn't have messed with my head. Well, the upside is the stream is going to probably improve now because I'm going to have less messing about with this stuff. I'm really not happy. Like in the previous instance of the stream, I was letting it kind of get to me. I wasn't speaking my way through absolutely everything that I was doing, because I was just trialing and erroring and just mentioning stuff and kind of literally grumbling. It wasn't great to watch. So hopefully, A, there will be fewer problems now because I'm more experienced with how this project works, and B, I am actually going to try, no matter how like grim it is, I will speak my way through everything. So this session makes it easier because I've just been talking again, just trying to get used to the next bit before I actually do it. But you know, those make for good streams because I'm speaking and I'm always speaking fairly clearly. But it's not so good in the sense of actually doing stuff, making progress, because there will always be bugs. They will always need to be fixed. It's fine. Carry on. And then think about whether the output matches your understanding of how your code should behave. Yeah, indeed. The last step is the most important. Of course, like, speaking the obvious much. To check if your code has race conditions, we spoke about those yesterday. Race condition is a situation where you don't know in which order two things that are independently concurrently executing are going to finish, and things change depending on in which order they finish. Like, say if something is saving to an address, to a point in memory, and something's reading from the same point, if one happens before the other, it will get the old value or the new value respectively, and if the thing doesn't exist, you'll get null pointer exception or some error. That kind of stuff can easily happen. So race conditions are dodgy, and really the difficult thing about like OG concurrency, when you're dealing with threads hands-on, getting it all dirty, race conditions are just not the one. They're like the biggest bane. And deadlock as well, which is when you get an unexpected state, which can be caused by a race condition, like I said, but it's a state where nothing happens and nothing will happen and you're dead. My favorite you're dead death sound effect is the Mega Man one. That one's the one that always terrifies me because it's just in an instance. I can't remember which Mega Man that's from, probably the second one, but I'm not sure if any of the others have the same sound effect like that. Boom, 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 boom. Should I just quickly look it up? Well, okay, finish this sentence, yeah? Goes race detector. So it gives you a fuck ton of helpful information for how to debug it. And of course it's going to be essential to know stuff because debugging concurrent code is so much harder than synchronous codes, which is what we've been doing so far. Let me just read this as well. The code we give you runs the workers as threads within a single Unix process. Okay, and can exploit multiple cores on a single machine. Some modifications would be needed in order to run it on multiple machines communicating over a network. The RPCs would have to use TCP rather than Unix domain sockets. Okay, there would need to be a way to start worker processes on all the machines, and all the machines would have to share storage through some kind of network file system. So this sentence about the storage is the only thing that kind of interferes with the way MapReduce is supposed to work. The fact that we don't care because all the files are always accessible. That's a simplifying assumption that comes from running everything on one computer. So we're not actually bothering with doing all the file system stuff. But that's fine. Simple is the way to go. Building up, We're going to stop before we've done everything, so in this project we're never going to have the file system working as it should, because it should rely on a different distributed systems algorithm, basically the whole global file system, Google file system stuff, which is, I guess, beyond the scope of this project. The MIT coursework doesn't deal with that. That's fine, you can stand on the shoulders of giants even without understanding things. Learn the next bit up. It's okay. But there would need to be a way to start worker processes on all the machines. Obviously that's easily possible. On one computer, if you're on a network and you have to make sure everything is started, you have to just send, I don't even know, how does that... Is it possible to send a request via the internet to start a program on a different computer? I'm sure there's a different protocol that handles that. Maybe RPC also does it, I'm not sure. But yeah, you would need that. Unfortunately, it doesn't say what that is. But it doesn't matter. This note is just how it is in the real world, so you have a bit of information. But it's pretty simple, very believable. I keep having to tap Dreg's Android because maps keep starting in the background and crashes, it keeps crashing, and so I have to keep tapping it in order to get it to keep working. For now the chat is still working, which is all good. But yeah, they don't call it Dreg's Android for nothing. Somebody told me this is basically a burner phone. I could use it to deal if I wanted to. Not that ideal, but I could if I wanted to, using this phone. Magic. Throw it in the Thames. You know how many people find working phones in the Thames, let alone dregs androids. The dregs of the Thames is what this phone is. Think of it that way. It's a piece of shit. What the fuck? Look at this. WhatsApp loaded in the background and then crashed. Why does this just keep happening? Google Play Store. Yeah, I'm gonna stop using this phone. I'm gonna switch to the chat app. I think it's called Chatty. You can have a desktop chat app that actually makes a sound whenever your stream gets a comment on it, a chat message. So probably gonna do that. Cool. Okay, that's it. So this is just our real world notes. This is whatever. Doesn't matter to us either. These are hints for how to debug. And we have, the information here about how RPC works, how call works. And some suggested testing. I do wish they structured this a bit more nicely, like put the test stuff in another color. This note as well. We know about call. Schedule is the one that we need to really learn about, so that's the one we're going to have to sit down and visualize. I think that will be the last thing I do today. Perhaps don't do any coding, but just get the head around what schedule does, now that we know what an RPC does, how it works. Right, so this is just a bit of introduction. We read through that, we know what it is. We have the master code and the worker code, as well as some RPC stuff, so this is the stuff we care about, schedule. So that's again. One thing, by the way, if you haven't done maths, you might not realize that well. If you haven't done something like maths is really the most extreme example of this. But you learn stuff by writing it down. Even if you can just read it, it's not going to go into your head nearly as much as when you write it down. When it comes to concepts, rewriting maths is doing maths to an extent. It's not as effective as problem solving, but it makes it stick in your head so much more. So whenever things get confusing, this is the way to do it. You write it out in notes. So let's have some notes on what schedule does. I'm going to open the pre-existing notes. I changed my mind, I'm not going to do that. That nice thing with Notepad, it always replaces what you're doing. Cool, okay, let's have a look. Your job is to implement schedule in MapReduce, schedule go. Master calls, maps crashed again. Calls schedule twice per job. The word job means a single instance of the entire MapReduce thing, like a single word count task, where we provided 8 files, but that's still a single task. Maybe think of it more as a single word count these 8 files task. Yeah, twice per job. Map phase, reduce phase. So schedule gets called for the map phase and the reduce phase, basically. What does it do? This is how it's called. What does it actually do? Hands out tasks to available workers. Really, what I'm doing when I'm making notes, I'm blueprinting everything, like the entire code, everything. It's even when you're coding, it is useful to not just get stuck in. Even for some of my algorithms, that I had an order relation type thing that determines when 2 raids are the same or not the same. When one raid supersedes another raid in the raid bot, the one that detects raids from the Pokemon Go scanner. And that's you know, the logic on that wasn't trivial. It took me I just sat down and wrote it out on paper using some flowcharts and shit to get the exact algorithm right. It's you know, the algorithm is along the lines of what type of raid is it? Has it hatched yet? Because hatch always follows egg. Those are the two phases of a raid, and then if it has hatched, then you check the. Well, no, first you check if it is even referring to the same hatch-egg pair by looking at the start time of the raid, and then you check the hatch, which triggers an update as well. And if that hasn't happened, then you skip the thing, because the way the data source works, it doesn't stream new stuff. It streams the full state of what's active over and over again, so you have to filter it using that kind of algorithm repeatedly to get the stuff that's actually new. Find the updates in the haystack, you know. Okay, hands out tasks to available workers. That's its job. Purpose. Call purpose. There will usually be more tasks than worker threads, so it gives each worker a sequence of tasks, one at a time. Like I said, that this is important. No buffering. Schedule should wait until all tasks have completed, then return. Returns when all tasks have completed. Yeah, I mean initially schedule knows all the map tasks before the map phase, and it knows all the reduce tasks before the reduce phase. So it has to send them out and wait for all of them to register as done, and then it exits. That's like the highest level conceptualization of what schedule is. Like if we split the code up, that's kind of what it looks like. Okay. Learns about available workers via register chan argument. Let's write arg. Yep, so there's a channel that gets passed into it that tells it. This is also kind of functional, the way that Go works with channels. You usually pass channels into functions, so the channel is it's like another piece of the puzzle. You connect it to the function by passing it into the function's arguments. Rather than other languages where you would probably think of the channel as being somewhere in the state, and then the function changes. It depends on the channels, but without explicit reference to them, so everything is a side effect, and it's not modular in the same sense. You can't just change the channel input if you change the channel, which is not the channel name or whatever. It's not necessarily that useful usually, but it just kind of gives you more of a more modular feel, more of a puzzly feel, a jigsaw puzzly feel. Cool. Yeah. Register chan, which yields a string for each worker containing its address. Some workers may exist before it's called, some may start while it's running, all will appear on register chan. Yeah, this is what I mean. So register chan, like I said, is outside the schedule, and it's passed as an argument to schedule. So it's important to have that here, because register chan cannot be inside, and it can be outside. Sorry, someone just said shit quite loudly outside. I wonder what happened. Might have stepped on a cat. That's probably not what happened. You would have heard like some next scream coming out of the cat if that had happened. No. Let's go with that's not what happened. Yeah, so register chan has to be outside of this thing, of schedule, or else it would only come into existence when schedule comes into existence, is called. but it just says here that it's possible for things to be in that channel before it's called, so that's not true. But yeah, it's passed as an argument, which means, you know, it references it explicitly rather than being a side effect. Do I mean side effect? Yeah, in some sense I do. I'm not going to clarify too much. Yeah, funny when I say something like that, it sounds kind of suspicious, but like I have my reasons for, you know, what I say, what comes out of my head. It just doesn't need to be clarified sometimes. Moving on. Yeah, all of them are coming through on register chan, and schedule should use all of them. That's absolutely not a problem. I'll just write it down as a note. Registers work as independently of schedule. Yeah, schedule should not have the round brackets because that's actually a call, an instance of calling schedule, but details, because this at least makes it look like a function rather than the word schedule. Maybe, you know, using quotation marks would achieve the same thing. Tells a worker to execute a task. Slightly pseudocodey way. To worker via equals worker dot do task RPC. Yep, arguments in do task args. Structure. Common RPC.go. This is just so I have a reference, so I don't have to reread this. File element is only used by map tasks and is the name of the file to read. Just writing that down, and oh yeah, schedule can find these file names in map files. So I'll do a second set of parentheses. Parentheses, of course, singular of that is parens, I think. I think it's the same word as parent. As in, that's the word it comes from. Should I just quickly look that up? A round bracket. Paren. Ah, I was wrong. It's actually paren and parens. It's an abbreviation. Oh, so parens is actually just... It's parenthesis and parentheses, of course. My Latin is slipping. Mad slippage on the Latin. But also, you know, parens, paren and parens is like an anglification of that. To use English S ending for plurals. Cool. Well, that is a thing. That is true. Still, I'm gonna have to investigate my microphone level because I'm always kind of scared that it's not loud enough. But like I can see even when I'm speaking quietly like this, I can actually see it's detecting it. It's just I'm wondering if it's audible, if it's clear. Is it clear? I'll check it out later, honestly. Let's move the camera in a bit closer. What's up, guys? have a shirt. Nudge the microphone. Have a shirt because have a new shirt on. Just so humid today. A new shirt and these pajamas as well. I don't know if the pajamas are visible. Nah, definitely not. I'm not bothered. That's it. Yeah. That's all the details we care about. I think I wrote down all the useful details. Okay, so the question is now, do I want to... Do you know what I will do? Because I forgot to do it when I said I would do it. I'm gonna play the Mega Man death sound. Wait just a second, I need to pause. Just got a knock on my door, so I'm just gonna mute myself. Cool, yeah, muted the, well, quick chat with my mum. She said there's pasta and I should not leave it too late, so I should wind this up. It's been 2 hours, you know. So yeah, let's have, okay, so this is Mega Man, am I reading this right? This is Mega Man X1. I think this is a different game. Yeah, that's definitely a different game. Sorry if that was too loud, and if it echoed, because of the microphone. This Mega Man 2, I'm pretty sure this is the game I'm thinking of. Just waiting for it. No. That was almost it. As in the... Not sure. I don't think it's exactly the one that I'm thinking of. Maybe it just gets played repeatedly or something. Where is the... Yeah, see that? People know. Mega Man 2. I'm spelling Mega Man wrong. Wow, embarrassing. I think it might actually be spelled with a space, I'm not sure. Really, Mega Man death sound effect is not... That's it. Okay, so it's the same it's the same as in Mega Man. Yeah, it's terrifying, isn't it? And yeah, the animation is just it's like the soul dissipates into 4 different locations. It just leaves. Okay, cool. Check it out. I am basically, yeah, I'm done with this. I'm gonna, quickly summary read this tomorrow, as in the first thing that we do. Gives each worker a sequence of tasks one at a time. Learns about available workers. This is worker register. That's how that works. This is the task to execute. And this is just the outline of what it does. Make it nice and line breaks, just to make it totally nice to read for myself tomorrow. Hands out tasks to available workers. Yeah, well, we know that shit. Master call schedule twice per job. Well, I mean, I'm an idiot. It would obviously it would have fit if I'd just done that. Yeah, and so this is all about schedule. You know, todo sobre mi madre. It's at the beginning of that film, the narrator says like, yeah, this doesn't really sound natural in Spanish. So it's a shout out to that film. Yep, I'll just call that schedule. Yeah, that's it. Do I want to? It's not like there are many details provided here. Schedule starts and waits for all tasks in the given phase to be announced or whatever, registered. Well, no, it gets called. Doesn't it get called whenever the tasks are done already? Yes, I'm not sure what it means by waits for the tasks. It just doesn't get called by the map files argument. Yeah, names of the files that are input to the map phase, one per map task, and reduce nip. Yields a stream of registered workers. Is the RPC address suitable for passing to call? Register chan will yield all existing registered workers, if any, and new ones as they register. Indeed, it's like if a worker crashes, well, we're not actually dealing with that quite yet, but if a worker crashes, the idea is that I guess register chan will receive it again when it comes back, and schedule will, I don't know, I'm not sure. We're just assuming nothing crashes for the time being. For part 3, and for part 4 things will crash. But yeah, that's the basic idea. And actually, I think, is there anything else here? All tasks have to be scheduled on workers. Once all tasks are completed, it returns code for part 3 and part 4 goes here. So part 3 is the first one. And there's already a bit of basic stuff here that just goes, it picks, we have n tasks and n other. So n tasks, why didn't they camel case this or like underscore it? Instead it's just never mind. So n tasks is the number of tasks. Don't forget, schedule will be called on map and reduce. So n tasks, if it's map, n tasks is map task number, n map, and n other is n reduce. But other way around, if this is called on reduce, n tasks is n reduce and n other is n map. Number of inputs for reduce or outputs for map. Yeah, inputs for reduce is n map, and outputs for map is n reduce. If I recall correctly. Inputs for map is 1-to-1 with the files, and outputs for reduce is also 1-to-1 with the files. Switch phase, yeah, phase sets them to the correct thing. So map phase, if it's in the map phase, n tasks get sent to the number of map files, and n other gets set to n reduce. Case reduce phase, n tasks get set to n reduce, and n other gets sent to the number of map files. Yeah, because this is... Wait, I'm confused. What did I say is going on? N tasks is number of inputs for reduce or outputs for map. So n other is n reduce. I would have thought here it would be n map. Okay, but n map is not in the signature. So what is n map? It's the number of map files. It should be the number of intermediate files for a given reduce file. So it should be able to detect that. Whereas obviously if you're in map phase and you're targeting the other, you have to set it explicitly, because there's nothing to detect, it's in the future. So you choose. So I'm guessing in this case map files is the number of input files coming from map. That's what n other is. N tasks is n reduce, the number of reduced tasks, but the number of map tasks is the number of input files. So I think map files is always going to take as an input the number of files. It's not completely clear. It holds the names of the files that are inputs to the map phase. In the case of the reduce phase, looking at this, I'm thinking it should hold zero? No, it says another is the number of inputs for reduce. Oh yeah, so it's nmap. But nmap is equal to nmap, the number of map files. Ah, this is, sorry. Yeah, it's me getting confused. Basically, I'm going to put it here just to make it completely clear that this is completely general. Nmap equals len map files, and that is always the case. So what I said about, you know, nmap and then reduce, in the map phase n tasks is nmap, in the reduce phase n tasks is nreduce, in the map phase n other is nreduce, in the reduce phase n other is nmap, and nmap, the number of maps, is determined by the length of the input to the entire algorithm. So yeah, we don't need to pass anything in to, I guess we should pass the input of the entire task into map files, even for the reduce, just so it can calculate nmap correctly. That checks out. You know, so map files is the input, and the length of that is nmap. Nreduce is the is nreduce, specified manually. Phase is the phase. Yep. Register channel is the register channel we were talking about earlier, and job name is the job name. So that deals with the entire signature. And then we have a couple of prints tasks. This is saying schedule n tasks, phase tasks, i.e. n map tasks, n reduce, however many reduce tasks, and n other is the other one, input and outputs, which should be the opposite of n tasks. Yep, and it does that whether or not it's map or reduce. And this, which is just the phase, is done. And that is the full code. Okay, we're fully familiar with the code, and I'm ready to end the stream. So literally all that happens is I do the code next sesh, and then jump straight into part 4 and do that as well, hopefully test them all without error. So I know I've not done anything today again, but I've set myself up. I think I may or may not be able to bash out the whole of MapReduce, finish it tomorrow. And then I might do another summary stream, because I spent an hour summarizing what's come before today, and then an hour and a half looking into the future. But I don't know, I might not. We'll see how it goes. That is it. Cool. Let's shut everything down. We've not really done anything today at all. Made some very minor changes with a new scrap file schedule. And the only changes I made to these, pretty much, other than that one comment that I put in, is to do the camel case conversion, as you can see. Yeah, that's the only change that has been made. And worker I edited as well, because there were loads of suggestions. So if I have to revert those because something has gone wrong, I do not know. But nonetheless, I edited it because it told me to, just so I could make the error go away. So it should be bloody equivalent if it's not. Certain man getting paxed. Cool. End of stream. I'm gonna say this is stream 4. End of stream 4. Ready to start 1.3, just to distinguish it from the other, because I've not made any real progress. Highly minor changes. Saved. Committed. Closed. Closed. That's it. Next sesh, as usual, 12 PM. I am going to try to get up earlier. Might do a bit of Skyward Sword today, just like an hour or so. I've done the Fire Sanctuary, so I'm just doing a bit of admin before moving on to the end of the game. You know, the last story section, the 7th bit. I think that's the last bit. I'm not entirely sure. 7th dungeon or whatever, because we've done 6 dungeons so far. So yeah, back at 12 p.m. And honestly, because of my 72-hour thing, I am going to try to get as far through all of the rest of everything as I possibly can. So next session is going to be hella doing compared to this one. All good guys. That is all that I have to say for today. Today's 2-hour and 26-minute stream. I am just narcissistically going to look at this. 0. Yeah. That's the sad thing about this kind of thing. You know, people would have to have infinite time to be able to engage in this kind of stuff. But that's the thing with streaming. You can't watch everything that someone streams, but you can, if it's interesting enough, you can just jump in and out. And this is obviously not that interesting because it's, you know, grinding your way through some coursework, literally. It's not as it requires, you know, commitment to understand, and that makes it not streaming not suited to streaming. But nonetheless, I'm hoping I can edit the best bits and just like present them, you know. That is it. Ciao.